I'll bet you that you've been asked at one point or another, what do you think the future is going to look like? And at one point or another, you may have said flying cars. Now, that would be pretty cool, and with quantum locking could actually become a reality. With the principle of quantum levitation, we could build vehicles, magnetic tracks, and even housing out of superconducting material. This is quantum levitation, where scientists use the principles of quantum physics to be able to make an object float over a magnetic source. No, there are no hidden supports. So, how does this work? Recently, I've become very interested in superconductivity, which is the property of materials to have no electrical resistance when cooled down to absolute temperatures. So, pretty cool. But for material to be superconductive, magnets need to be cooled to insanely cold temperatures. And because magnet cooling can only work if cooling fluids are consistently circulated to keep a material displaying those superconducting properties, a ton of energy is consumed. And it takes a lot of time to maintain these temperatures. These materials only superconduct when kept below a certain temperature, referred to as the transition temperature, and that's generally below liquid nitrogen temperatures. So as you can imagine, it would be a whole lot more easy if they could operate at room temperature. That is being worked on with high temperature superconductors. These operate closer to room temperature than liquid nitrogen, and they are a lot easier to run and manage and are also more efficient and can carry more current. Right now, they still operate at pretty cold temperatures, but that is being worked on. Now, superconductors hate magnetic fields, unlike regular conductors. They repel the magnetic force from the inside by producing small amounts of current on their surfaces, called vortices, which expel the magnetic field, leaving us with none at all. And that's actually the basic foundation of the Meissner effect. So because of superconductors' hatred for magnetic fields, they normally just float in a kind of wobbly and unsure manner. We want to find a way to prevent this, and clearly we have. And that's because of quantum locking, or flux pinning. Because these high-temperature superconductors are extremely thin, there are small imperfections that permit some magnetic channels, which are flux tubes. They lock the magnetic field in all three dimensions, and that is how we achieve stability, and allow the superconductors to be pinned above the magnet. Then that stiffens the wobbly attribute of the Meissner effect. And by the way, these superconductors that I am talking about are type 2 superconductors because these are the category that high-temperature superconductors fall into. Type 1 superconductors, on the other hand, can actually be penetrated by magnetic fields unless they are super thin, which is possible but less likely. And remember, we need magnetic penetration because this is what allows us to do quantum locking. The combo of the Meissner effect and vortices result in some pretty cool behavior, which allows us to levitate superconducting magnets and play around with them in some pretty mind-blowing and entertaining ways. And now you might be wondering, what are the barriers? Well, quantum locking definitely isn't perfect, because generally over time there's actually a degradation in the high-temperature superconductor's property because of what we call flux creep, which creates a pseudo-resistance and decreases critical fields and current density. And that's actually what I'm working on solving right now, so I will keep you updated with my latest projects in that. So that was a little introduction to superconductivity for you, flux tubes, the Meissner effect, and quantum locking. I hope you learned a little bit, and if you have any questions, please reach out. Thank you so much.